Hello there, and welcome to our unit on solutions. Now, solutions are mixtures of substances where you can't see the different parts, so they're homogeneous, and they're all around you. These are a few I found around my house, right? That's some tea, which you can't see the different parts of once it's dissolved. This is some window shining or mirror shining solution that's been mixed up, and you can't see the different parts. These are a bunch that you might find in a lab. Some of them are colored and others are colorless. But regardless, they all have a lot in common, and we're going to be learning more about them throughout this unit. So some things that are solutions are some solids like the brass in this door handle here. The brass has both zinc and copper, but they are mixed super well together at the atomic level, and you can't see the different parts to it. Liquid solutions, so things like vinegar, where you have acetic acid, which is one of our organic acids, and it's in there mixed with lots of water. It's only, I think it's about 7% acetic acid. I don't think it's, oh yeah, it says it on there. If you got good eyes, you can see 7% acetic acid. Air is a gaseous mixture. So you have one of these things and you spray it. It's just compressed air. And so air has things in it like mostly nitrogen and some oxygen and a little bit of carbon dioxide and a few other trace gases that are out there. But yeah, definitely a mixture that can't see the different parts, so also qualifies as a solution. So the parts of a solution, I think most people have heard of before. The part that dissolves, the part that's in the lower quantity is called the solute. And the thing that does the dissolving, the thing that's in the greater quantity, is the solvent. And then when you mix them together, when you make your tea, that's a solution. So solute plus solvent equals solution. There you go. When you make a solution, obviously there are different amounts of solute that you could put in there. If you only have a trace amount, like if you only leave the tea bag in there for a few seconds, you would call that a dilute solution. And then one that has a lot more solute dissolved in it, that will be termed concentrated. So the more solute particles that dissolve, the more concentrated it will be. Or the other option is if you evaporate or remove some of the solvent, you can make something more concentrated that way. The solutions that we're going to spend most of our time using in this course are going to be aqueous solutions. So aqueous just means that water is the solvent. That's the most common that you're going to run into. The reason why water is such a good solvent is because of its polar bonds and its shape. Which give it a negative side on the side with the oxygen and a positive side, slightly positive on the side where there's the hydrogens. And so that means it's going to be attracted to both positive ions and negative ions when it comes to ionic compounds. And if you have molecules that are polar, if they also have oxygens and hydrogens in them, then they will also dissolve very easily in water. So that's the great properties of water that make it such a good solvent. So when ionic compounds dissolve in water, what happens is that they become hydrated, fancy word for surrounded by water molecules. And if you remember, the oxygen has that negative side and the hydrogen has a slightly positive side. So the negative side is going to be attracted to all the positively charged ions, so you'll get water molecules surrounding all the sodium ions in here with all the oxygens pointing inwards, right? Because oxygen is the negative side of that molecule. And with the chlorine, it'd be the opposite. You'd have the hydrogens facing inwards because they are more positive, and so that orientation will work for the chlorines. So it doesn't matter what type of ion it is, as long as there's strong enough attraction to those water molecules, they'll all be hydrated, they'll get surrounded by water, and you'll end up with an aqueous solution. What happens is that the ions separate, and so you can show that as an equation. That's what this little dissociation represents. So you start off with this solid up here, and then as soon as it was dissolved in water, the little AQ, those ions separate and are now floating around separate from each other. Molecules are very similar. If they're polar, they're going to be attracted to water and dissolve as well. This little representation here is of some glucose molecules as a solid to begin with because they're all stacked together, and then they too can be surrounded by water molecules because of the attraction of these little OH groups on the glucose to the OH groups on the water. And so, yeah, water makes a really good solvent for things like sugars due to them both being polar. Now, nonpolar things can also dissolve, but just not polar things. They have to dissolve other nonpolar things. So if you've ever made salad dressings before, this is the beginnings of a salad dressing I was making, you'll notice that the oil doesn't like to mix with, what is this, lemon juice? And at the bottom here I have some maple syrup. So they're all kind of separated right now based on their density, but once I mix this up, these two are fairly polar. They'll mix together no problem, but the oil won't. The oil might dissolve some other ingredients from your salad dressing that might be oily as well, but not polar things like your sugars or acids in lemon juice. Finally, there's a group of really cool molecules that called surfactants, which are surface acting agents, that are really good at helping non-polar things mix with polar things. So a great example of this is the soaps you use when you're washing your dishes. They have a polar part to their structure, like that's represented by these little red balls. So this end is polar. And then they have this tail, which I don't have orange, but I'll use yellow. They have this tail to them, and we can look at the structure of this later if you like. But the tail part is non-polar. So the tail part will be attracted to oily things, like the oil in the salad dressing there. And because the other end of the molecule is polar, it will be attracted to the water. So you'll end up with this oily blobs being surrounded by these surfactant molecules. And so soap molecules are good examples of that. So soap molecules all have this polar side that faces out towards the water, and the non-polar that faces inwards toward the oils. And that's what makes them so good at cleaning your dishes and getting this oily gunk off the surface of your plates.